Ever wondered what we're really made of? From tiny viruses to colossal galaxies, everything around us is made up of mind-blowing stuff. We humans, viruses, plants, and animals share something special with those majestic galaxies, planets, and stars out there. In the vast expanse of the cosmos, there exists a hidden universe teeming with particles so tiny yet so incredibly powerful that they shape the very fabric of our reality. These mysterious entities are known as elementary particles. These teeny-tiny building blocks come together to create you, me, and everything in the universe. From the earliest theories of matter to the cutting-edge discoveries of modern physics, scientists have relentlessly pursued the secrets of these elementary particles. By decoding their properties and interactions, we gain a deeper understanding of the universe and unlock the door to technological advancements that were once unimaginable. In this video, we're going to get a detailed breakdown of elementary particles. So, without wasting any time, let's jump right in. Elementary particles, also known as subatomic particles, are the fundamental constituents of matter and energy. They are the building blocks that make up atoms and all other particles in the universe. First, let's explore some of the basic subatomic particles. Electrons. Electrons are negatively charged particles that orbit the nucleus of an atom. They have a very small mass compared to protons and neutrons and are considered almost massless. Electrons are crucial for chemical reactions and the formation of chemical bonds. Protons. Protons are positively charged particles found in the nucleus of an atom. They have a mass approximately 1,836 times greater than an electron. Protons carry a positive electrical charge that balances the negative charge of electrons, making atoms electrically neutral. Neutrons. Neutrons are electrically neutral particles also located in the nucleus of an atom. They have a mass similar to protons, making them collectively referred to as nucleons. Neutrons play a crucial role in stabilizing atomic nuclei by counteracting the electromagnetic repulsion between protons. These three particles, electrons, protons, and neutrons, form the basic structure of an atom. However, scientists have discovered numerous other subatomic particles with different properties and roles. The field of subatomic particles has experienced significant expansion and advancement, particularly with the development of powerful particle accelerators designed to investigate high-energy collisions involving electrons, protons, and other particles interacting with matter. Within this field, the current understanding is organized within a framework called the Standard Model. The Standard Model is a conceptual framework that classifies and describes all known subatomic particles based on theoretical models of the fundamental forces that govern matter. Let's take a look at this chart. Elementary particles are divided into elementary fermions and elementary bosons. All elementary particles are either bosons or fermions. The classification of elementary particles into bosons and fermions is based on their quantum statistics. Fermions adhere to Fermi-Dirac statistics, while bosons follow Bose-Einstein statistics. Furthermore, their spin characteristics can be distinguished using the spin statistics theorem, with fermions having half-integer spins and bosons having integer spins. It is a quantum mechanical property and does not correspond to the actual spinning motion of the particles. Fermions are usually associated with matter, whereas bosons are generally considered force carrier particles. However, in the current state of particle physics, the distinction between the two concepts is unclear. Weakly interacting fermions can also exhibit bosonic behavior under extreme conditions. Elementary fermions are divided into quarks and leptons, and both have corresponding antiparticles that are antiquarks and antileptons. There are 6 types, or flavors, of quarks: up, down, charm, strange, top, and bottom. For every quark type, there is a corresponding type of antiparticle, known as an antiquark, that differs from the quark only in that some of its properties, such as the electric charge, have equal magnitude but opposite signs. Quarks also have a property called color charge, which comes in 3 types: red, green, and blue. It is important to highlight that these terms are just labels. Quarks are much smaller than the wavelength of visible light and do not have any color in the normal sense. Antiquarks have the same color as their quarks but are represented as anti-red, anti-green, and anti-blue. There are 6 types of leptons, grouped into 3 generations. The first-generation leptons, also called electronic leptons, comprise the electron and the electron neutrino. The second are the muonic leptons, comprising the muon and the muon neutrino, and the third are the tauonic leptons, comprising the tau and the tau neutrino. For every lepton flavor, there is a corresponding type of antiparticle, known as an antilepton, that differs from the lepton only in that some of its properties have equal magnitude but opposite sign. Elementary bosons are divided into gauge bosons and scalar bosons. Gauge bosons have spins of 1 and 2 and are associated with the following interactions: photons, electromagnetic interaction, W and Z bosons, weak interaction, gluons, strong interaction, and the graviton, which is hypothetical and associated with gravity. Scalar bosons are a single kind, represented by the Higgs boson, and have a spin of 0. The development of particle physics was made possible in the 20th century with the advancement of increasingly sophisticated instruments capable of probing matter at extremely small scales, on the order of 10 to the power of -15 meters or less, that is, at distances comparable to the diameter of the proton or neutron. However, the foundational concepts and philosophy of particle physics can be traced back much further, to ancient Greece around 500 BCE. During that time, the Greek philosopher Leucippus and his student Democritus proposed the concept that matter is composed of tiny, indivisible particles called atoms. These early atomists hypothesized that atoms were the fundamental building blocks of all matter and were invisible to the naked eye. Despite the groundbreaking nature of their ideas, the concept of atoms was largely neglected for over 2,000 years. Instead, the prevailing view held that matter was made up of 4 elements: earth, fire, air, and water. However, by the beginning of the 19th century, the atomic theory of matter had experienced a resurgence in popularity. The work of British chemist and physicist John Dalton played a significant role in strengthening atomic theory. Dalton's studies suggested that each chemical element is composed of its own distinct type of atom. His atomic model proposed that atoms were indivisible and had specific properties that determined the behavior of different elements. Dalton's atomic theory formed the basis for the modern understanding of atoms. In 1896, Henri Becquerel, a French physicist, made the landmark discovery of radioactivity. He found that certain materials emitted radiation spontaneously without any external influence. This discovery opened up a new field of study and challenged the prevailing notion of atoms as immutable and indivisible. In the subsequent year, J.J. Thomson, a physicist at the University of Cambridge in England, conducted experiments that provided evidence for the existence of subatomic particles. Thomson's experiments involved investigating the properties of cathode rays, which are streams of electrons emitted from a negatively charged electrode in a vacuum tube. By measuring the deflection of cathode rays in electric and magnetic fields, Thomson determined that they were negatively charged particles with a much smaller mass than that of hydrogen, the lightest known atom at the time. This groundbreaking discovery revealed the existence of the first subatomic particle, the electron. Building upon these advancements, Ernest Rutherford and Frederick Soddy, while working at McGill University in Montreal, made significant contributions to the understanding of radioactivity and atomic transmutation. In 1902, they observed that certain radioactive elements decayed over time, transforming into atoms of different elements. This discovery shattered the idea of atoms as immutable and indivisible entities, providing clear evidence that atoms can change and transmute into different types of atoms. In 1911, Ernest Rutherford conducted an experiment known as the gold foil experiment, which provided crucial insights into the structure of the atom. He discovered that most of the mass of an atom is concentrated in a tiny, dense nucleus at the center. This revelation challenged the previously held idea of the atom as a uniform and indivisible entity. Rutherford proposed a new model for the atom, likening it to a miniature solar system. According to his model, the negatively charged electrons orbited around the positively charged nucleus, much like planets orbiting the Sun. This concept of electron orbits explained how the atom remained stable despite the electrostatic attraction between the positively charged nucleus and the negatively charged electrons. Niels Bohr, a Danish theorist, further refined the atomic model in 1913 by incorporating the concept of quantization, which had been introduced by German theoretical physicist Max Planck. Planck's work demonstrated that electromagnetic radiation, including light, occurs in discrete packets of energy called quanta or photons. Building on Planck's quantization idea, Bohr postulated that electrons orbit the nucleus in fixed orbits or energy levels. Each orbit has a specific size and energy, and electrons can transition between these orbits by either emitting or absorbing quanta of energy. This theory provided a framework for understanding the stability of atoms and the emission and absorption of light at specific wavelengths. This concept helped explain various atomic and subatomic phenomena and gained wider acceptance in the scientific community. This understanding laid the groundwork for further advancements in the field of particle physics, leading to the development of more sophisticated models and theories to describe the behavior of subatomic particles and their interactions. The concept of quantization, which emerged in the early 20th century, led to the development of quantum mechanics and provided a successful framework for understanding the structure of atoms. Niels Bohr's model proposed that electrons in atoms move only in specific orbits characterized by fixed values of angular momentum, each associated with a quantum number that takes integer values. However, in the 1920s, Samuel Goudsmit and George Uhlenbeck, Dutch physicists, recognized that a fourth quantum number was necessary to fully explain the spectral properties of alkali metal atoms such as sodium, which have one outer valence electron beyond the main core. Goudsmit and Uhlenbeck introduced the idea of an internal angular momentum, or spin, associated with electrons. They suggested that electrons possess a spin quantum number that can have two possible values, -1/2 and +1/2. This spin corresponds to the intrinsic rotation of the electron, as if it were a spinning electric charge. It implies that each electron generates its own magnetic field and has a magnetic moment. The orientation of this internal magnet with respect to the magnetic field of the rest of the atom can be either parallel or antiparallel, resulting in two quantized states and two possible values for the spin quantum number. Spin is now understood as an inherent property of all subatomic particles. It is a fundamental characteristic used to classify particles into two main groups, fermions and bosons. Fermions have half-integer values of spin, 1/2, 3/2, etc., while bosons have integer values of spin, 0, 1, 2, etc. In the standard model of particle physics, matter particles such as quarks and leptons are fermions, while force-carrying particles like photons are bosons. 2 years after the work of Goudsmit and Uhlenbeck, the English theorist Paul Dirac provided a sound theoretical background for the concept of electron spin. In the development of quantum mechanics, Paul Dirac played a crucial role by incorporating Albert Einstein's theory of special relativity into the framework of quantum theory. His work provided a solid theoretical foundation for the concept of electron spin. Dirac's relativistic theory of the electron revealed that, in addition to its orbital motion around the nucleus, the electron must possess an intrinsic angular momentum called spin. Spin is a quantum mechanical property that gives rise to the magnetic moment of the electron. When Dirac applied special relativity to the electron's behavior, he derived an equation that described the allowed energies of the electron. However, this equation had a peculiar feature. It had two solutions, a positive solution and a negative solution. The positive solution corresponded to what was already known as normal electrons, but the negative solution appeared to describe electrons with a positive charge, which seemed contradictory. In 1932, Carl Anderson made a significant discovery by observing the particle known as the positron, which resolved the mystery surrounding the negative solutions in Dirac's equation. Positrons are very similar to electrons in terms of their mass and spin, but they possess the opposite electric charge. These positrons were the first antiparticles to be experimentally observed, confirming Dirac's prediction. Dirac's theory, which incorporated special relativity in quantum mechanics, applies to all subatomic particles with a spin of 1/2. Consequently, all particles with this spin value are expected to have corresponding antiparticles. Antiparticles have the same mass and spin but possess opposite charges and other quantum numbers compared to their corresponding particles. However, it is important to note that matter cannot be built from both particles and antiparticles. When a particle encounters its corresponding antiparticle, they annihilate each other in a process known as annihilation. During annihilation, the total mass of the particle-antiparticle pair is converted into energy in accordance with Einstein's famous equation E equals mc², where E represents energy, m denotes mass, and c is the speed of light. In the everyday world, there is an excess of electrons, protons, and neutrons compared to their corresponding antiparticles, positrons, antiprotons, and antineutrons. The absence of significant amounts of antiparticles in normal matter allows for the formation and stability of atoms as well as the complex structures that constitute our everyday world. Natural positrons do indeed exist, and they are created through high-energy cosmic rays that originate from outer space and interact with particles in Earth's atmosphere. Cosmic rays consist of energetic subatomic particles, such as protons and other atomic nuclei, that travel at significant speeds. When cosmic rays collide with atomic nuclei in the atmosphere, they generate extensive particle showers. The immense energy carried by the cosmic ray is transformed into various forms of matter, in accordance with Einstein's theory of special relativity, E equals mc squared. Among the particles produced in these cosmic ray showers are pairs of electrons and positrons. These electron-positron pairs are created due to high-energy interactions and conservation laws. However, positrons have a very short lifespan and survive for only a fraction of a second before they encounter electrons. When a positron and an electron come close to each other, they annihilate, resulting in the complete conversion of their combined mass into energy. In particle accelerators, physicists are able to recreate high-energy collisions that mimic the interactions occurring in cosmic rays. In 1955, a significant breakthrough occurred in the field of particle physics when a team led by Emilio Segre and Owen Chamberlain conducted experiments at the Bevatron, an accelerator located at what is now the Lawrence Berkeley National Laboratory in California. They were searching for evidence of antiparticles, specifically antiprotons. The experiment involved colliding high-energy protons with target atoms. In these collisions, some of the energy was converted into new particles. Segre and Chamberlain's team observed the creation of particles with the same mass as protons but with opposite electric charges. These particles were identified as antiprotons, the antimatter counterparts of protons. Shortly after the discovery of antiprotons, another team working at the Bevatron discovered the antineutron. The discoveries of antiprotons and antineutrons in particle accelerator experiments provided experimental confirmation of the existence of antimatter. Since the discovery of antiprotons and antineutrons in the 1950s, physicists have made further progress in understanding the fundamental particles that make up matter. Since the 1960s, studies have revealed that protons and neutrons, which were previously considered elementary particles, are composed of even smaller particles called quarks. Quarks are point-like particles with fractional electric charges and a property called spin, which determines their intrinsic angular momentum. Protons and neutrons are composed of 3 quarks each. The combination of different types of quarks gives rise to the different properties and behaviors of these particles. Similarly, antiprotons and antineutrons are composed of antiquarks, which are the antiparticles of quarks. Antiquarks have opposite electric charges compared to quarks and exhibit the same fractional spin. Neutrinos, on the other hand, are elusive particles with very little mass and no electric charge. They also possess spin of 1/2. Just like quarks, neutrinos have corresponding antiparticles known as antineutrinos, which have opposite properties. The understanding of particle interactions and decays led to the realization that certain conservation laws govern the behavior of quarks and leptons, particles like electrons and neutrinos. One such law is the conservation of lepton number, which states that the total number of leptons minus the total number of antileptons remains constant in any interaction. This means that if a lepton, such as an electron, is produced in a decay process, an antilepton, in this case, an antineutrino, must also be produced to balance the lepton number. In addition to the familiar particles like protons, neutrons, and electrons, scientists have discovered the existence of more than 200 other subatomic particles. These particles, often referred to as extra particles, are not commonly observed in everyday low-energy environments but emerge under the higher energies found in cosmic rays or particle accelerators. The behavior and variety of these additional particles have been explained through the framework of quarks and leptons, which are fermions. With just 6 types of quarks and 6 types of leptons, along with their corresponding antiparticles, physicists can account for the diverse range of subatomic particles and their behaviors. This understanding forms the basis of the Standard Model of Particle Physics, which provides a comprehensive framework for describing the fundamental particles and their interactions. In the next part, we will explore the fascinating world of bosons, the force carriers that mediate the interactions between particles. Bosons play a crucial role in the fundamental forces of nature, such as the electromagnetic force, the weak and strong nuclear forces, the gravitational force, and even the elusive Higgs boson.